Today we're going to talk about solving exponential and logarithmic equations. Let's recall some information from previous knowledge. If f of x equals a to the x and g of x equals log base a of x, if you recall, they are inverses of one another. Remember what it means to be an inverse. When you compose the two functions together, either way, you're going to have everything completely cancel and you'll be left with your original input x. So f of g of x equals x and g of f of x equals x. So using f of x equals a to the x and g of x equals log base a of x, if we compose them together, log base a of a to the x equals x, and a raised to the log base a of x equals x. If the base of the logarithm and the base of the exponential function match, they cancel. If the base of the exponential function and the base of the logarithmic function match, they cancel. So we'll start off with a few simplistic examples of solving exponential and logarithmic equations. So for each of these, we're going to solve for x. So 4 raised to the 2x minus 7 equals 64. Think back to the one-to-one property. If a to the x equals a to the y, then x must equal y. So if we could rewrite 64 as a base 4, which is 4 to the third, like bases set equal to each other, their exponents must be equal to each other. So we can set the 2x minus 7 equal to 3 and solve for x. Add 7, divide by 2, and we would get x equals 5. Remember, when you solve equations, you can check that your answer works by plugging x equals 5 back into the original equation and making sure you get a true statement. Let's do another one. 3 raised to the 3x minus 2 equals 81. If there was a way we could write 81 as a base 3, then we could set their exponents equal to each other. Well, 81 is 3 to the 4th, so we can set 3x minus 2 equal to 4 and solve for x. Add 2 to both sides, divide by 3, and we get x equals 2. What about this example? E to the x equals 9. How do we write 9 so that it's exactly e raised to a power? The problem is we can't. Up here, we could rewrite it so that the bases match 3 and 3 to the 4th here, but down here, I don't know what e, which is approximately 2.71828, is raised to what exact power gives you 9. So if you recall from previous knowledge, a logarithmic function is going to undo an exponential function. So keeping the log base, the same, this is base e, so we'll take a log base e. And if you recall, a log base e is one of our special logarithms, the natural log. Remember, you can do whatever you want to an equation as long as whatever you do to the left-hand side, you do to the right-hand side. So what if we took the natural log of both sides? Remember, the natural log is log base e. So the base of the logarithm is e, the base of the exponential function is e, so they're going to cancel each other. The natural log and the e will go away, and we're left with x equals the natural log of 9. And then you can plug that into your calculator to get a decimal approximation if you'd like to. Let's do another one. E raised to the 2x plus 1 equals 11. Again, I don't know what e raised to what exact power would give us 11, but I know how to get rid of a base e. I would take a log base e, which is the natural log. So we'll take the natural log of both sides. The base of the logarithm and the base of the exponential function match, they cancel. And we are left with 2x plus 1 equals the natural log of 11. Now we can subtract 1 from both sides and divide both sides by 2. And you can plug this into your calculator if you'd like to get a decimal approximation. Just remember, your numerators are automatically assumed to be in parentheses, so if you're going to put it in your calculator in one step, make sure you put parentheses around the natural log of 11 minus 1, and then divide that whole thing by 2. So now let's get into some more in-depth examples. We'll start by solving strictly exponential equations, then we'll move to solving logarithmic equations. So here, e to the 2x squared equals e to the 3x minus 1. Notice these two exponential functions have the same base, so the one-to-one property says we can just set their exponents equal to each other. 2x squared equals 3x minus 1. Get everything on one side of the equal sign, 0 on the other, factor, and then set the factors equal to 0. And we get two solutions, x equals 1 and x equals 1/2. Now here, 4 times 3 to the x equals 20. Remember your order of operations. Exponents come before multiplication, so you cannot distribute that 4 to the 3 to make it 12 to the x. So instead, we're going to divide both sides by 4 to get rid of that 4. Then we'd have 3 to the x equals 5. Well, now the variable that we're looking for is up in the exponent, so we need to make the base 3 go away. What's going to make an exponential base 3 go away? A log base 3. And you can do whatever you want to an equation as long as you do it to both sides. So we'll take log base 3 of both sides. Now the base of the logarithm and the base of the exponential function match, they cancel. And we have x equals log base 3 of 5. If you needed a decimal approximation of that, most calculators don't have a log base 3 button, so we would turn it into a natural log or a common log, which are the common logarithmic buttons on a calculator. So we do the natural log of 5 divided by the natural log of 3, which gives us approximately 1.465. 3 times e to the 2x plus 9 equals 36. Solve this like any other equation. Isolate the variable. It just so happens that the variable is in the exponent, but we'll worry about that as we get closer. First, we'll get rid of this plus 9 by subtracting 9 from both sides. This is 3 times e to the 2x, so we'll divide both sides by 3. And now we need to get rid of the e. To get rid of an e, we'll take a log base e, which is natural log. So we'll take the natural log of both sides. Then we're left with 2x equals the natural log of 9. So x equals the natural log of 9 divided by 2, which you can put into your calculator to get a decimal approximation. Okay, let's do one more exponential equation. 4 times 6 raised to the 2t minus 3 minus 7 equals 2. Solve this like any other regular equation. Isolate the variable. Start by adding 7 to both sides. Now remember, exponents come before multiplication, so we cannot distribute that 4 to the 6. So instead, since that's 4 times 6 to the 2t minus 3, we'll divide both sides by 4. Now we need to get rid of that that exponential base 6, so we'll take a log base 6 of both sides, and we have 2t minus 3 equals log base 6 of 9/4. Add 3 to both sides, and then divide by 2. Now, if we needed a decimal approximation of this, we would have to turn this into either common logs or natural logs. So we'll turn it into natural logs. And so then I would do the natural log of 9/4 divided by the natural log of 6, figure out what that is. Then add 3, figure out what that is, and then divide the whole thing by 2. If you want to put it in your calculator in one motion, make sure you put the entire numerator in parentheses. And you would get a decimal approximation of about 1.7263. Now let's talk about solving logarithmic equations. We'll start off with some simplistic examples and build up to more complicated ones. So log base 7 of 3x minus 11 equals log base 7 of 2x plus 17. Notice the bases of the logarithms are the same. Logarithms are one-to-one just like exponential functions are, so if the bases are the same, their insides must be equal to each other. Now this is just a regular multi-step algebraic equation with variables on both sides. Subtract 2x, add 11, and we get x equals 28. Now with logarithms, remember we have a restriction that you cannot take the logarithm of a negative number and you cannot take the logarithm of 0. So the only thing that you can take the logarithm of is a positive value. So you do a quick check. If you plug 28 into this logarithm, make sure you get a positive number, which you do. And if you plug 28 inside of this logarithm, make sure you get a positive number. So with solving logarithms, you need to do a quick check just to make sure when you plug it back in, it doesn't give you a negative value or 0. Let's do another one. Here we have the log of x equals 2. Remember, no base, the base is automatically assumed to be 10. That's your common log. So what's going to make a log base 10 go away? An exponential base 10. And remember, you can do whatever you want to an equation as long as you do it to both sides. So I'm going to take a big base 10 and raise it to the log of x on the left-hand side. So I would have to take a big base 10 and raise it to the 2 on the right-hand side. So now, notice, this is now a one-to-one exponential equation. The bases are the same, so their exponents must be the same, which is how we started. But now the base of the exponential function and the base of the logarithmic function are the same. They cancel. And we're left with x equals 10 squared, or x equals 100. We have the natural log of x equals 7. To get rid of the natural log, remember that's log base e, we would need an exponential base e. So I'm going to take a big base e and raise it to both sides. E to the natural log of x equals e to the 7. The base of the exponential function and the base of the logarithm are the same. They cancel, and we're just left with x equals e to the 7, which you can put that in your calculator to get a decimal approximation if you need to or would like to do so. We had log base 2 of 3x minus 1 equals 3. The variable is inside the logarithm, so we need to make the log base 2 go away. So we're going to need an exponential base 2. So I'll take 2 and raise it to the left-hand side, and take 2 and raise it to the right-hand side. The base of the exponential function and the base of the logarithm match. They cancel. So I have 3x minus 1 equals 2 to the third, which is 8. Add 1 to both sides, divide by 3. And remember, when solving logarithms, quick check, if you plug 3 in here, make sure you get a positive value. Log base 3 of 2x minus 1 equals 4. Same thing, the x is inside the logarithm, so we need to make the log base 3 go away. So we'll take a big exponential base 3. Raise the 3 to the log base 3, they would cancel. 3 to the fourth, and we're left with 2x minus 1 equals 3 to the fourth. 3 to the fourth is 81. Add 1 to both sides. Divide by 2, we get x equals 41. 2 times 41 minus 1 is a positive value, so the answer works out. Here's a little bit more in depth. Solve it just like any other equation. Isolate the variable. So we'll start by getting rid of the 17, so we'll subtract 17 from both sides. This is 4 times the natural log, so we'll divide both sides by 4. And now the variable is stuck inside a logarithm, so we need to make the natural log go away. Natural log is base e, so we'll take a big exponential base e. Raise this side to e, raise this side to e. The natural log and the e cancel, and we're left with 3x minus 2 equals just e to the 1 power, or e. Add 2 to both sides, and divide by 3. If you're going to put this in your calculator, remember to keep your numerator in parentheses. Most calculators are automatically designed that e is going to be raised to a power, so you'd put a 1 in for the exponent, and you would get a decimal approximation of about 1.5728. Let's do another one. Similar thing. First, start by getting rid of the 32. Subtract 32 from both sides, and you get 18. Now we'll get rid of the 6. Divide both sides by 6. Now what's going to make a log base 3 go away? A big exponential base 3. I'll raise 3 to the left-hand side, 3 to the right-hand side. The log base 3 and the exponential base 3 will cancel, and I have 4x minus 9 equals 3 to the third, or 27. Add 9 to both sides, and divide by 4. Quick check, when I plug 9 in, 4 times 9 minus 9 gives me a positive, so the answer does check out. Now this one's different because it's got 2 logarithms being subtracted. We don't just have a logarithm equal to a value. So what we need to do, all the other ones we had was a logarithm equal to a value. So what we'll do here, based on previous knowledge, is actually just condense this into one logarithm. Working backwards from our logarithmic properties, 2 logarithms with the same base being subtracted can be written as one logarithm with their insides being divided. Now we can make the log base 4 go away with a big exponential base 4. And remember, to raise to the 1/2 power is square rooting. 4 raised to the 1/2 would be the square root of 4, and we would have x over x minus 1 equals 2. Get that x minus 1 out of the denominator by multiplying. Distribute the 2 and solve for x. You would get x equals 2. Plug 2 into this logarithm, it checks out. Plug 2 into this logarithm, it checks out. It didn't give you a negative or 0, so that answer actually works. Let's do one more example. Here again we have multiple logarithms. Now before, if we had 2 logarithms with the same base being set equal to each other, we could set their insides equal to each other. The problem is these are 2 logarithms being added. It's not just logarithm equals logarithm. So let's combine this into one logarithm. 2 logarithms being added can be condensed into one logarithm with their insides being multiplied. Now the base of the logarithms are the same. We can set their insides equal to each other. Distribute this out by FOILing, and then get everything on one side of the equal sign, 0 on the other. X squared plus 5x plus 6 equals 0. Factor, and set the factors equal to 0. However, when we plug in -2, it checks out here, but -2 plus 1 is -1. That's not going to work. Same thing when we plug in -3, so it turns out this has no solution. That's it for solving exponential and logarithmic equations. See you next time.